Start the study of a new algebraic structure called quotient rings. And in this particular video, we're going to look at a specific example of a quotient ring. And it's given this name, and that's read as Z mod in Z. And so the first thing that I want to do is kind of define the situation of what we're looking at here. The first thing is we want to recall that Z under its ordinary addition and multiplication is a ring. And we also want to recall that in Z, which is just the set of multiples of n, is a subring of Z. And in fact, in Z is actually an ideal. And I do want to talk a little bit about what that means, so let's just review what that is for just a bit. In other words, what we've got is that for all elements of the set Z, and for every element inside NC, we can show that A times L, which just happens to be AL because the integers are a commutative ring, that element belongs to the subring. And this is actually quite easy to prove. L inside NZ is going to imply that L is equal to Q times N for some Q inside the set of integers. And so when we are looking at AL, that's just now A times QN, and that will be A times Q times n, which is clearly an element of NC. So we do indeed have an ideal. Now, what I want to do is I want to define a certain set, and this set is actually based on another thing that we've looked at in a couple of videos. So I also want to recall that we have defined a congruency mod a subset, mod a subring, and in our case the subring is going to be in Z. And the congruency mod in Z relation is defined on the set of integers by A is congruent to B mod in Z if and only if A minus B belongs to the subring in Z. Of course, what this means is that A minus B is a multiple of n. So A minus B is a multiple of n, and that actually means that this congruency mod in Z relation happens to be exactly the same as congruency modulo the integer n. Now, the thing that I want to remind us of is that we already know something about these kinds of relations. We showed in a previous video that congruency modulo any subring is an equivalence relation. And we've even showed that the equivalence classes, so we know that the equivalence classes for this particular relationship are the left cosets of the subring. And our subring, of course, is in Z. So in other words, the equivalence classes are going to be things that look like A plus in Z, and that is a set that looks like A plus K times N, where K is running over all of the integers. And when you look at that set long enough, you realize that the set A plus in Z is nothing more than the set of things that I'm going to call L that happen to be integers, such that A is congruent to L mod n. And so we actually wind up with exactly n equivalence classes in this particular case. And what are those equivalence classes? Well, we know exactly what they are, and I'm going to write them as 0 plus n times z, 1 plus n times z, 2 plus n times z, all the way up to n minus 1 plus n times z. And these wind up being a partition for the set of integers. So these partition the set z, meaning that in each and every integer is in exactly one of these particular sets. We also know something else, and that is that a plus nz is equal to b plus nz. They are the same equivalence class if and only if a minus b is part of the subring n times z. Now, what we want to do next is we want to ask the question about whether or not we can form a ring out of these left cosets. So just to give ourselves a little bit more notation, I'm going to say that the set z mod nz, that's how that is read, this is going to be the set of left cosets of the subring n times z. So in other words, z mod nz is nothing more than the set containing 0 plus nz, 1 plus nz, 2 plus nz, all the way up to n minus 1 plus nz. And so the question is can we define a plus and a times on z mod nz that turns the set of left cosets into a full-fledged ring? Now, I don't want to get overly involved in trying to do something really, really weird and strange, so we're going to look at the obvious things to try. And the obvious thing to try for the addition is to look at the left coset, a plus nz, and add to that b plus nz, and see if we could write that as simply a plus b plus nz. And likewise, the obvious thing to try for multiplication is to think about a plus nz times b plus nz being equal to a times b plus nz. Now, the big question that we have to look at is this. Since each left coset has multiple names, are these operations well defined? And I kind of want to tie this video up with what do I mean by are these operations well defined? So, in other words, if I know that a1 plus nz is the same left coset as a2 plus nz, and I know that b1 plus nz is equal to b2 plus nz, is a1 plus nz plus b1 plus nz, which is defined to be a1 plus b1 plus nz, is that particular coset the same as a2 plus nz plus b2 plus nz, which our definition would say is a2 plus b2 plus nz. In other words, are these two left cosets the same? And likewise, we ask the same question about multiplication. So we have to say, is A1 plus NC times B1 plus NC, which is defined to be A1 times B1 plus NC, is that particular left coset the same as A2 plus NC times plus NC, which would be defined to be A2 times B2 plus NC. And so our final question is, are these two left cosets the same? We will explore this question in much more detail in the next video.